Good morning, general physics. You ever forget where you are for a moment? So, I hope you're doing all right. Let me remind you that what I told you guys last time. Your next exam is not a week from this Friday. It is a week from this coming Monday. All right. So I moved it into the future one class meeting time. All right. So on Friday we got a recitation session. I'm going to check the sign-up sheet, and I'll check it tomorrow afternoon and see how many of you have signed up. If I mentioned this last time, if we're not taking full advantage of that time, I might have to reconsider how we use that time. Okay, so if you plan to come on Friday, please sign up. And I'll check that tomorrow afternoon, Thursday afternoon, and see how we're doing. All right, so good morning, everybody. Hi, Tristan. Hi, William. Hi, Holly. Let me think. Is there anything else I want to tell you before we get started? Lab quiz. Lab quiz has a picture in it, and some students aren't able to see that picture, so I'm baffled at this point. We've had the same problem on exams, and what I've done is taken that picture, which has free body diagram options, and I've posted it under resources, and this is on the laboratory Sakai site. Resources, labs, week 6. All right, so when you get to that problem, can't see the picture, it doesn't load, there's just a little icon saying there's supposed to be an image there, but you don't actually see it. Go to the resources labs week 6 folder, and it's in there. All right, so in the future I'm just going to attach pictures instead of trying to embed them. Then you can click a little link and they open up in a different browser window. Okay, so there's 2 homework problem sets that are posted concurrently. They're not due on the same day. But they're posted concurrently because I think you can work on problems from both of these problem sets sort of out of order, and so read through both problem sets, and then when you are maybe in lecture we say something, talk about something that relates to something you read about in the problem set, you'll be ready to do it. All right. All right, gang. Is my tech going to work today? Looks like it. All right, it's working. How's my battery doing? Hello, computer. All right, what's going on here? Oh, sorry guys, my power cord is too short today. All right, here we go. Okay, gang. So we were talking about potential energy last time. Let's recap all of the new physics that we've learned in the realm of energy and work. Well, maybe I should have said work and energy. Okay, so let me write out the integral definition of work, the most general form that we have. Work is defined as the dot product between a force and a displacement. But maybe I should do this first. If you have an infinitesimally small displacement, dr, the corresponding infinitesimally small, I like saying that word, infinitesimally small amount of work done would be the dot product between the force and the displacement vector. And we call this a scalar product because the result of a dot product is a scalar quantity. It's a kind of product between two vectors, and actually, you know, maybe I'll write this out. The way you calculate the magnitude of this thing is the magnitude of the two vectors multiplied together times the cosine of the angle between them. So another way you can think about this is these dot products are, and this might be useful for you. You know, we can think of a force as having an x component, a y component, j hat, and a z component, fc k hat, and a displacement vector as having an x component, a y component, and a z component. And the dot product between these two vectors, written in this unit vector notation, is the product of the x component of the force and the x displacement plus the y component of the force times the y displacement plus the z component of the force times the z displacement. So it turns out that it is a scalar quantity, but that's just another way that you can calculate it. All right, so I'm digressing a little bit here, but that's a useful thing. If you guys, where would you see that in math? Some of you will advance through math. I don't know. I don't know if I saw dot products, and there's another vector product called the cross product, or the vector product, and that's we'll see that later this semester. And where did I learn that? I don't think well, I'm not sure I ever saw that in a math class. Maybe calculus 3. I don't know, but or linear algebra maybe. Linear algebra is such a fun course. All right, anyway, so if you have an infinitesimally small amount of work done from this infinitesimally small displacement dr, the total work that you would have over a path, try writing that again, is an integral. Integrate along a path for this thing, and that gives you the total amount of work. All right, so we talked about that last time, and in practice, you know, if it's a one-dimensional case, a lot of times the amount of work done for a one-dimensional force, or let's say the force is constant and the direction of travel is straight, the amount of work done can be just thought of as, instead of an integral, a dot product between two vectors, f and delta x. That's if, you know, so that's if f is constant, the force is constant. Oops. F is constant, and delta x is well, I guess this would work if it's 1 or 2D. Well, I guess it doesn't really matter then. I guess it's only if f is constant. If f is constant, you can factor it out, and then the integral over the path is just the length of the path. So delta x would be a distance instead of like this. I guess you would think of that. Delta x is the distance along the path. All right, so some things that we learned earlier. We learned that if you think about the total amount of work, and I could write it like this or like this, the total amount of work that's done by a net force, the total forces acting on an object, that's equal to the change of kinetic energy, where kinetic energy is another scalar quantity, 1/2 v squared, 1/2 mv squared. So this is energy of motion. All right, energy of motion. And it depends on the mass of the object, but it depends on the velocity squared. And so double the velocity, you quadruple the amount of kinetic energy. And so we derived that by thinking about a shopping cart that was acted upon by a net force in the absence of drag or friction or any other force. So the applied force was the net force, and we calculated this. I'm getting updates. We calculated what the total work done by this net force would be, and we got this quantity, 1/2 mv squared. All right. So and then we looked at, well, what if the force is one of these forces that we call conservative forces, and we looked at the case of gravity near the Earth's surface. And the point of doing that was showing that the work done by the force of gravity going from point A to point B didn't depend on the path. You could go, directly up the incline, or you could go over and then up. It doesn't matter what path you take, the total work done by gravity is the same. And if you go back to where you started, the total work done by gravity is 0. It does negative work in one direction and positive work in the other direction, but the total amount of work for that whole path would be 0. So, this is really different than, let's say, friction. Friction. If I had a refrigerator, and I push it from one side of my kitchen to the other, and then push it back, friction is going to do work, negative work, when I go across the room, and it's going to do more negative work when I go back. So the path that I take matters, and it also you don't end with a situation where if you go on a closed path you get back to 0 total amount of work. So conservative forces are these special things, and we saw that when you have conservative forces, I'll call that W sub C, doing work, the amount of work they do is associated with a potential energy, a change in potential energy. And the relationship is the work done by conservative forces equals the negative change in potential energy. And we saw that, I'll write this a little bit out, U sub grav for gravitational potential energy is a quantity equal to the weight of an object times its vertical height. We'll call that y. Could call it h, call it y. And so this number, it's a number you can calculate, but it depends on the what you say y equals 0 is. And if I say y equals 0 is sea level, then places here in West Virginia would have a vertical height of 400 feet ish. But if my y equals 0 point is defined as the roof of Byrd Science Center, then we probably are all at negative height at this moment relative to that height. But it doesn't matter, because what really matters when it comes to potential energy is not its value in an absolute sense, what the number is, but how it changes when you go from one place to the other. That's why in this formula for the connection between potential energy and work, what we have is a change in potential energy, a delta. All right, the delta is what matters. So let's derive another kind of potential energy. Let's come over here, and we'll look at the spring force or elastic force. All right, you guys know about this now. You did a lab on it last week. The spring force or elastic force. The law, the force law that describes the spring force is called Hooke's law. It says the force that a spring exerts is called restoring force is equal in magnitude to some constant k, spring constant, times the amount of stretch that the spring has. So draw a little picture here. If I have here's a spring, and there's a mass attached to it. So if I say that, you know, this position that it's at right now is its equilibrium position, and then I stretch it out to some other position, x, final, while this thing is being stretched, okay, it's stretching out, the displacement it's experiencing is in this direction, right? It's being displaced to the right, but the spring force is pulling it back. Okay, so we have a situation like this. And, okay, so if we look at the amount of work, the infinitesimally small amount of work that's done when you move a very small distance called dx toward the right, it's equal to this force dotted into that displacement, dx. And so here, or in other words, f s dx cosine of the angle between those two vectors. So if you have, you know, one vector that points this way and one vector that points this way, the angle between them is 180 degrees. And the cosine of 180 degrees is -1. All right, so important lesson here. When you have a force that opposes the direction of motion, the direction of displacement, either in this case completely or partially at some angle, if there's a component of the force that projects onto the direction of displacement and it points in the opposite direction, then that force does negative work. And that's fine. It's a scalar quantity. It can still be positive and negative, but remember here, the negative sign doesn't mean direction. All right, the negative sign means that well, it's related to direction. It means that you have two things that point in opposite directions, okay, and you get negative work. So kind of tuck that away for now. What does it mean to do negative work? What does it mean to do positive work? Well, when we put these pieces all together and look at the complete picture, the equation, which was called the work-energy theorem, we'll know. We'll see what's happening. All right. So this spring does negative work in this case. And how much work does it do? Well, I have to integrate from the equilibrium position, x, to the final position, this thing. Okay? Well, the spring force is kx, so let me put that in there. And I'll pull the negative sign out in front. So here I have the limits of integration being x's as well. So it's customary when you do that to kind of use a dummy variable inside the integrand. So I'll call that's not x to the first power, that's x prime. Okay, and when you integrate, so the k is a constant, I can pull that out. So I have negative k integral from x naught. I'm just going to put a 0 there to x k x prime. Nope, sorry, I didn't. The k is gone. The k is gone. X prime dx. So this is an integral where you're integrating with respect to x, and it's doing differentiation of a polynomial backwards. So instead of multiplying the x by the exponent and subtracting 1, you add 1 to the exponent and divide by the new exponent. So this becomes, the negative k is still there. The integral of x prime with respect to x, I should put a prime on that too, is, so it's x to the first power becomes x squared. The prime is really confusing here. I should have picked something else. Divided by 2, you get 1/2. evaluated from 0 to x. Well, you evaluated 0, you get 0. You evaluated x, you get 1/2 x squared. So the result you get here is the amount of work done by this spring force as you're stretching the spring is negative 1/2 k x squared. And back over here, work done by conservative forces are equal to a change in potential energy. And this is a conservative force. And you could convince yourself that this is true because if you reverse things and go from the maximum stretch back to 0, the amount of work done would be exactly the opposite. So the total would be 0. All right. So we learned that the work done by conservative forces equals a change in potential energy, a negative change in potential energy. So here we have negative delta U equals negative 1/2 kx, or delta U, let's put an S underneath it, is equal to 1/2 kx squared. The negatives cancel. And you know, it's customary to say that the amount of spring energy you have when x is 0 at equilibrium is 0. So at any other point, the amount of energy you have is just 1/2 k x squared. So you could think about it as a change, or in this case, the 0 point is well defined. So you can think about it in absolute terms as well. So now we have two kinds of potential energy. We have potential energy associated with springs and potential energy associated with gravity. All right, so spring force and gravity. But that's a good example of why the definition of work in its most general form is an integral, because you can have a force that changes as you go from one place to another. It's a positionally dependent force. Next week, 2 weeks from now, when you guys do the computational lab, part of it is exploring well, how do you put Newton's second law into a computational model? That's the first part. The second part is, well, now you can actually model situations where the force isn't constant but is positionally dependent, and I'm going to do that with gravity for satellites. And then you can also look at situations where the force is velocity dependent, and that is air drag. Okay, so you know, really interesting things happen in the real world when you have forces that aren't constant but are actually dependent on position or some other thing like velocity. All right. All right, so we're not done yet. We can put all this together now, though. Let's come over here. So everything over here is an aside. It's important, but let's come back over here. Let's record our final result. I could write U elastic or U spring. We find that that's equal to 1/2 k x squared. Looks a lot like potential energy, doesn't it? 1/2 k x squared, but it's not the same. It's a k, not an m. It's an x, not a v. Put that in its box. Maybe I'll put kinetic energy in a different colored box. All right. And okay. So we have total work equals changing kinetic energy, and work done by conservative forces is negative change in potential energy. We can put all this together now and get a final result. If I have the total amount of work done, I could break that into work done by conservative forces plus everything else. The work done by, let's call it N sub C, non-conservative forces. Try to make my W's all look the same. Okay? And so what we have here is from the very first day, we saw that the total amount of work done is change in kinetic energy. So I can put delta K on that side. The work done by conservative forces is a negative change in potential energy. So I can put that in there. And then I get WNC. Now let's move everything, all the energy terms to the left-hand side. All right, and we get change in kinetic plus change in potential equals the work done by non-conservative forces. And so on this left-hand side here, what we have is a sum equal to what's called mechanical energy. Mechanical energy. And so let me define this a little bit more carefully here. So mechanical energy, E, is equal to the sum of kinetic energy and potential energy. All right, mechanical energy equals kinetic plus potential. And what we have up here is the work energy theorem, our final version of the work energy theorem. I think that's right, theorem. Change in mechanical energy equals the work done by non-conservative forces. Okay, so now we're going to see, why is it called conservative? Well, imagine you have a situation where there's no non-conservative forces. And so what does that mean? It means no friction, air drag, applied forces, people pushing, that sort of thing. If that's true, then the work done by non-conservative forces equals 0. In which case, the change in mechanical energy also equals 0. So this follows from what I have over here. And if that condition is met, what we say is mechanical energy is conserved. Mechanical energy is conserved. So what I'm saying is that in the absence of non-conservative forces, the total amount of kinetic and potential, this thing I'm calling E, mechanical energy, never changes. It doesn't change. The total amount doesn't change. Now it can move back and forth. I think what we'll do on Friday is we'll watch a lot of videos. I got a ton of video demonstrations for energy. And I can, field some questions on homework and stuff like that. But I'd like to show you some of these videos. They're all in the lab. I don't have them outside the lab. But maybe I'll try to broadcast on Zoom. I think I can do that. I can show. It won't be that great, but we'll do that again. I mean, it won't be that great quality, but you should be able to see and participate, maybe even. So we'll do that on Friday. But the way I picture it here is picture energy as it's a number, and it's sort of like accounting, where you have numbers in different places. But if mechanical energy is conserved, those numbers always balance to the same thing. They always add up to the same thing. So you can have situations where maybe picture buckets filled with water, and the water represents energy, and you have a bucket for kinetic and a bucket for potential, and kinetic energy can go to it can move back and forth. Kinetic can become potential, potential can become kinetic, but if mechanical energy is conserved, the total amount of kinetic plus potential equals 0. So, equals this a constant. The change in E, delta E, is 0. So the prototypical type of question that you'll see conservation of mechanical energy conserved to or applied to are things like a pendulum swinging back and forth. Think of a pendulum. A pendulum, you're getting sleepy. The pendulum has energy of motion, but when it rises up, that energy becomes potential, gravitational potential energy, because it's getting higher. And then it falls, so it's losing potential, gaining kinetic, gaining potential, losing kinetic, gaining kinetic, losing potential, gaining potential, losing kinetic. And it oscillates back and forth, back and forth. So systems that oscillate may have this property of total mechanical energy being conserved, but there's still a lot going on. The energy is being converted back and forth. So remember when I said work, the way I like to think conceptually about work is not a force applied over a distance or the dot product between a force and a displacement vector. I mean, yeah, that's how you calculate it, but that doesn't really mean much to me conceptually. But what does mean something to me conceptually is work is energy changing forms. And so in the case of the pendulum going back and forth, and let's ignore air drag, right? Air drag is a non-conservative force. It would cause the pendulum to slow down and eventually stop, to lose mechanical energy. But in the absence of air drag, what you have is the only force doing any work is gravity, which is a conservative force. And when the pendulum falls, gravity does positive work. And when the pendulum rises, gravity does negative work. So the pendulum loses potential, gains potential, loses potential, gains potential, loses potential. So work is being done by a conservative force. What does that mean? It means this object has energy, and that energy is changing forms. It's going back and forth from kinetic to potential, from kinetic, potential, kinetic, potential. But the total amount is the same because it's conserved. It's a conservative force. All right, I'm getting a little excited. I think energy is probably my favorite topic in first semester physics. Anyway, the total amount of energy is conserved if there's just conservative forces. If there's non-conservative forces that do work, like the pendulum with air drag, it's going to slow down and eventually stop. Why? Because the air drag is friction and it does negative work. It's a non-conservative force that does negative work. Look at the formula here. Right here. If there's a non-conservative force that does negative work, WNC is negative, delta E is negative. What does that mean? Mechanical energy, E, is decreasing. It's losing energy. The system is losing energy because there's a non-conservative force that does work. All right. The system loses energy. The universe doesn't. That energy isn't lost to the universe. Where does it go? What the heck happens? And what do you think happens to the energy? Put it in the comments. And while you're thinking about that, maybe I'll try and see if my where is it? I have the ability, I know I do, it does change form, William. It does. But it's not like, so when the pendulum's going back and forth, its energy is changing forms from kinetic to potential, but that energy stays with the pendulum. It's conserved. It stays with the pendulum. All right, it's changing forms, but it's not moving from one object to another. So when non-conservative forces are acting, are doing work, then that is what is happening with energy is the energy is moving. It's being transferred from the object that it starts with to some other object. Leaves the system. It does leave the system, Tyler. It becomes it is imparted on the molecules of air that are traveling over the object. And in our macroscopic world, how does that manifest itself? Those molecules get warmer, their temperature increases, but microscopically, temperature is kinetic energy. So as the pendulum swings and plows through the air molecules, it imparts energy, kinetic energy, onto those air molecules. And they're buried in here is a lesson which is sort of like, yes, it can be expelled as something like heat. So the heat is the flow of energy from, we call it thermal energy in our macroscopic world, the flow of thermal energy from one place to another. And in the case of this system of a pendulum, the pendulum's kinetic energy is being transferred to the air molecules, and they're heating up. They're gaining thermal energy, because thermal energy is really what it is microscopic kinetic energy. Those molecules move faster because they're heating up. So the insight that we gain here is a lot of the distinction that we make between conservative forces and non-conservative forces is really a distinction between things that we can keep track of in the macroscopic world, like how fast a baseball is traveling, or how fast a pendulum is traveling and how high it goes, or another prototypical example, roller coasters. How fast is it going? What are the hills that it's going over? You know, in the macroscopic world, we can keep track of those things. What we can't keep track of is individual air molecules and their kinetic energy. So a lot of what we call conservative versus non-conservative forces is really, can we keep track of where that energy goes? And we can't really keep track of the energy being transferred to trillions of air molecules. So what we do is we throw up our hands and we call that temperature. We say, oh, well, temperature is a measure of the average kinetic energy of those molecules, but we're going to forget what each individual one is doing. So Tyler, if I may, why is it that when you move air with a fan, it is cooler than warm then? So what you're experiencing there is, if you had like a well-insulated room, meaning heat couldn't flow in or flow out of that room, and all that was in there was a fan, that fan would heat up the room. Slowly, but it would heat up the room. The temperature of the air in that room would get warmer. The same would happen with a refrigerator. If you had a well-insulated room and you put a refrigerator in it with the door open, that would heat up the room. Because yes, the refrigerator inside is getting colder, but at the expense of air outside, which is getting warmer, and more energy is being imparted to the outside air than is being removed from the inside air. You don't get something for nothing. And so the reason a fan makes a room feel cooler is because of evaporative cooling. When you have air moving over your skin, you know, if you have moisture on your skin, it evaporates. Even when you're not sweating, there's moisture on your skin, or near your surface of your skin. So when water evaporates, there's a phase change. It moves from liquid to gas, and that takes a lot of energy, and that energy is pulled away from your body, and so your skin cools off. Your skin cools off. So that's why moving air feels colder. It's not that it actually is. Temperature-wise, it's not cooler air. It's just that the dynamic of how it interacts with your skin and the moisture on your skin is very different. So, what are we doing on time? We got 10 minutes. So, what do we want to do? I don't know. I don't know if I want to start anything new. Let's take a look at, well, let me think here. Maybe let's kind of like let's think of the work energy theorem for a specific situation. All right, so the specific situation is this is interesting. I think it's interesting. Let's think of the situation of a skydiver. A skydiver, so the skydiver jumps out of the plane. Skydiver is going to accelerate for a while, but we know that eventually the skydiver is going to reach terminal velocity. Okay, and so here's the skydiver. Sorry, all I can draw is stick figures. That was supposed to be that was supposed to be the parachute. Let's try that again. I'm horrible. Yeah, that's good enough. So the skydiver is falling. So as the skydiver is falling, it's experiencing a displacement in this direction. There's a force of air drag, call that F sub g, that's in that direction, and there's a force of gravity, the skydiver's weight, which is pulling it down. So we know that, all right, one of these forces is conservative. It's associated with the force of gravity. F of g, so there's potential energy associated with it. The other force is non-conservative. All right, so you got one conservative force, one non-conservative force, and the work energy theorem says as the skydiver is falling, the change in mechanical energy is equal to the work done by non-conservative forces. And we can write it out a little bit more. The change in mechanical energy is change in kinetic plus change in potential equals the work done by non-conservative forces. Okay, so my question to you, all right, so now you're going to have to be a little interactive here for the last 5 minutes. All right, so get your chat window ready to answer this question. So we said that this thing is happening at terminal velocity. All right, it reaches terminal velocity. What does that mean? At terminal velocity, v is constant. All right, so which one of these terms in the work energy theorem is 0 as the skydiver is falling? I know I got to pause for a while because there's like a 10-second lag between me saying something and you seeing it. Holly isn't very kinetic? Question mark. Tyler says atom. Um, so Holly's right. Kinetic energy is 1/2 mv squared. So if the if the velocity is constant, kinetic energy is constant, which means change in kinetic. If kinetic energy is constant, the change in kinetic is 0. All right. Okay. So what kind of work is gravity doing? Or let me just ask, gravity is doing positive work here, because gravity is pulling down and the displacement is down. So the displacement vector and the gravitational force vector point in the same direction. So the dot product would give us a positive number. What's happening to delta U? What's happening to the gravitational potential energy? All right, so your options are, over here, just a little bit. All right, your options are delta U is 0, gravitational potential energy is not changing. Delta U is less than 0, it's decreasing. Or delta U is greater than 0, gravitational potential energy is increasing. So, which is it? Less than, greater than, or equal? Tyler's got it, Maggie's got it, Chris has got it. Good. So, gravitational potential energy is mgy. So as you're falling, y is decreasing. So the gravitational potential energy is decreasing. So the answer here is right here. All right, so we think about the work energy theorem now with these two facts. That means the work being done by the non-conservative force of drag is equal to the change in potential energy, because delta K is 0. Delta K is 0, so the work done by the non-conservative force of drag is equal to the change in potential energy. So this symbol-wise, sign-wise makes sense, because the drag force points up, the displacement is down, so the drag force does negative work because it points in the opposite direction of the displacement. All right, how much work does the drag force do? The exact, for a given distance that the skydiver falls, the amount of work that the drag force does is exactly equal to the change in potential energy. All right, it's exactly equal to the change in potential energy. So I like to think of this as, so what's happening to the energy? Make this a little smaller. Oh, almost out of time. Of the skydiver. Well, what we have is, as the skydiver falls, we have potential energy becoming kinetic energy, and the kinetic energy is being dissipated as heat or thermal energy. Okay? And the rate at which the kinetic energy is, so you have potential becoming kinetic as the skydiver falls, and kinetic becoming heat, or thermal energy, I shouldn't say heat, because the air molecules are heating up. And what the work energy theorem says, that at terminal velocity, the change in kinetic energy is 0. So that means the rate at which potential energy is becoming kinetic is exactly equal to the rate at which kinetic energy is becoming thermal energy and being dissipated into the air. They're exactly the same. So energy is flowing through this system as the skydiver falls. The stored up potential energy is becoming kinetic, and the kinetic energy is being dissipated into the environment as thermal energy at exactly the same rate. that is being converted from kinetic potential to kinetic. All right, so this is how you can use the work energy theorem even when there's non-conservative forces. All right, so that's it for today. I will see you guys on Friday in some way, shape, or form. All right, so again, if you're going to sign up to come in person, please do that by tomorrow afternoon so I can see how many people to expect, and if there's good participation, we'll do it as usual. If not, maybe we'll do something different. All right. Will we be able to complete all of the homework by Monday with this information? Yes. You have all the information you need to complete all of the homework in both. Well, let me back up. There's one other topic, and that's the topic of power. And power, it's not that. I mean, it's not that much new to understand. But everything else, you have all the tools. So Friday or Monday, we'll talk about power, and then you'll have all the tools you need to do all the problems. But will you be able to? You might need a little bit more practice. So that's what we'll do next week. We'll focus on doing lots of examples, including some of the homework problems. All right. All right, guys. I'll see you guys on Friday.